Hello, everybody. Today we're going to do the part 2 of the quantitative electrolysis. So in the previous video, which I will leave a link somewhere around here, all right, so part 1, I have covered how do we calculate the mass volume of product is being formed or liberated at your respective electrode. All right, so that will be like more of a forward type of calculation. So in this video, we're going to do with the part 2. I'm going to cover everything that got to do with the backwards, which is question give you mass, the volume, or the number of moles of product that's being formed. Are you able to calculate back what was the, for example, time of the electrolytic experiment, or maybe what is the ampere use, all right, or perhaps how many Faraday was involved, all right, in your experiment. Okay, so now let's look at the first one where we're going to look at how do we calculate time, all right, given from this question. So we look at summer 20, paper 41, question 3C. So a current of 2.5 times 10 to the power negative 5 ampere is drawn from this cell. Calculate the time taken for 0.1 gram of lithium electrode to be used up. Assume the current remains constant throughout the period. Now for lithium, first thing first is lithium equation is Li plus electron to give 1 mole of lithium solid. All right. And we calculate the number of moles being formed first. 0.1 gram divided by 6.9. The number of moles formed is 1.45 times 10 to the power negative 2. Okay, this is your experiment. Now let's look at theoretically here. Theoretically, we have 1 electron needed to form 1 mole of lithium. In other words, we need 1 Faraday, which also is 96500, to form 1 mole of lithium. So currently now you only have 1.45 times 10 to the power negative 2. Okay, so how much quantity of charge is being passed? So let's put this as X. Okay, so X equals to 1.45 divided by 1 times 96500. So we only obtained 1399.25 quantity of charge. All right, so 1399.25 of quantity of charge resulted to 1.45 10 to the power negative 2 moles deposited. All right, now, so Q is the total quantity of charge that was being passed in your electrolysis or electrolytic experiment. So Q equals to IT, which is 1399.25, which is also I times T. All right. So since the ampere given in the question is 2.5 times 10 to the power negative 5, so the time is 1399.25 divided by 2.5. So I've calculated to 5.6 times 10 to the power of 7. Okay, in seconds. So this would be 5.60 times 10 to the power of 7 seconds. All right, so that's how we work backwards, all right, to calculate time. Now we shall look at another example here. This question asks us to calculate the current, all right? Similar, but the question is just different. Okay, now let's look at Winter 22, paper 42, question 3B. So molten magnesium salt is electrolyzed for 15 minutes by a constant current. 4.75 times 10 to the power 22 magnesium atoms are produced at the cathode. So cation ion moves to the cathode. So first, we bring out the equation for magnesium. So magnesium requires 2 electrons to form 1 mole. Now, theoretically, we need 2 Faraday to liberate 1 mole of magnesium solid. Okay, so currently now your experiment gave 4.75 times 10 to the power 22 magnesium atoms. So for atoms, you need to convert to mole by dividing by the Avogadro constant, which is 6.022 times 10 to the power 23. So the number of moles over here would be, just let me calculate for a while. 6.022. So this would be 0.789, okay, 0.0789 moles. So your experiment, so this is your experiment, you obtain 0.0789, okay. Now, can we work back? What is the quantity of charge passed? Okay, so therefore, X equals to 0.0789 divided by 1 times 2 Faraday, which is so the total quantity of charge passed in your experiment is 15,223 coulomb. Okay, now 15,223 coulomb, all right, is the quantity of charge, which is equivalent to IT. So I is the question mark, T is the time, which is 15 minutes. You convert it to seconds times 60. So your ampere or your current is 16.9. Okay. All right, 16.9. There you go. Okay, similar, but it's just that instead of asking time, they ask for current. Now let's look at another one, a bit more challenging. This time, calculate the charge. Okay, now first, the charge, all right, is the number of Faraday, remember? So for example, just now magnesium is 2E, therefore it's 2 Faraday. Okay, yeah. Now lithium is 1E, therefore it's 1 Faraday required per mole of solid. So now you have N number of mole of electron, which also means you need to calculate the N number of Faraday. Is it 1, is it 2, or is it 3? Because why? The number of Faraday is the number of charge on the unknown, which is here. Okay, yeah. Now, so chromium is a transition element, so it can exist in variable oxidation state. So we don't know what's the oxidation number of chromium. It can be 2, it can be 3, it can be 6. Okay, but we have to go and calculate it. Okay, so now let's look at what the information given. Now, first, current is 1.8 and 40 minutes. So let's calculate the experiment quantity of charge. 1.8 times 40 minutes times 60 to convert it to seconds. So 1.8 times 40 times 60. So this will be 4320, okay, quantity of charge. Okay, and then that would be your experiment. And it was found this quantity of charge gave this much of chromium. All right, so what is the atomic mass of the chromium? Let me just look. Chromium is give me a moment. I was thinking chromium data booklet. Chromium is 52. Okay, so we divide by 52. Okay, so what is the number of moles? 0.0149. Okay, so what we have obtained here is that in your experiment, you pass 4320 coulomb of charge and you obtain 0.0149 moles of chromium. Okay, so therefore, can we work back now? 1 mole of chromium, according to this relationship, requires how many or how much quantity of charge? So 1 divided by answer times 4320. So according to the answer here, my calculation, 289484. Okay, now, so this is theoretically how much quantity of charge required to deposit 1 mole based on the relationship given from the experiment. Now then, we divide this number with 96500, right? Because we want to see how many times of Faraday constant is inside this number. Okay, so we take this number, we divide it by 96500. I got 2.9998, which is 3. Beautiful number. So that means 289484 was actually 3 Faraday. Okay, now 3 Faraday means 3 electrons. So in other words, N is actually 3. Why? Because Cr3 plus 3 electrons to give 1 mole of chromium. And this is the 3 Faraday that we calculated in experiment base. 3 mole of Faraday will give 1 mole, okay? Which also means it is 289484 quantity of charge will only give 1 mole. All right, so that's how we calculate the charge on the unknown. Okay, so that is another pattern that can come out. Now let's proceed to another example here. Calculate the oxidation number. Okay, so first, calculate the oxidation number. Actually, it's the same thing as calculating the number of Faraday. Why? Because the oxidation number, all right, which is like just now, chromium N plus N Faraday. So the number of Faraday is equivalent to the oxidation number, or so-called the charge on your element. Okay, so let's look at summer 1841, question 3. Oxide of iron dissolved in an inert solution, electrolyzed for 2 hours using a current of 0.8. The electrolysis products are iron and oxygen. The mass of iron produced is 1.11. Calculate the oxidation number of iron. Okay, now, so we don't know what is the iron oxidation number. Maybe it can be Fe3 plus, maybe it can be Fe2 plus. All right, so maybe, okay, this is iron N plus, do not know how many N electrons to form 1 mole of iron. So that is the relationship. Okay, so first we calculate how much quantity of charge. Q equals to IT, which is 0.8 times 2 hours, convert to minute, convert to seconds. So this is 5760. 5760 coulomb, all right, gave how many moles of iron? So you obtain 1.11 gram. Can we calculate the moles of iron? Okay, so what is the atomic mass of iron? Iron is 55.8. Okay, so therefore, the number of moles is 0.01989. So based on the experiment values, we know that 5760 gave us 0.01989 mole of iron. So let's ask ourselves, to obtain 1 mole of iron, how much quantity of charge is needed? So 1 divided by answer times 5760, 289556. All right. And this is the total quantity of charge needed to give us 1 mole. Okay. And we divide this with 96500 to see how many Faraday is this. The answer is 3.00. So hence the oxidation number of Fe oxidation number is +3. Okay. ON oxidation number is +3. Okay. Very similar to the question previously. All right. So I think that is all. Okay. For the part 2 quantitative electrolysis. So if you have any special question that you want me to discuss, please do text me. All right. Leave a comment and I'll get back to you.